All right, guys. Well, here are your notes for the effects of exercise on cardiovascular disease and type 2 diabetes. Now, remember, these notes are not covered in the material for exam 3. They will be part of the new material on exam, or on the final exam. Actually, the only new material on the final exam, since the obesity notes are not on there this time um, around. And yeah, and I'm really giving these to you now so you have all the way up from now until the end of the semester to start working on your concept map, your final concept map on paper, because you really need the information from these notes to be able to complete your concept map. So get into these, start looking at these, start working on your concept map, and you should be good to go. All right, so this is just a really cool image that was in a research article that I saw. You don't need to know the details of this. This is very complex, but pretty much what this shows is that all the different effects that skeletal muscle have on the whole body when you're using that skeletal muscle to exercise. Everything from neurogenesis to neuroplasticity to decreased inflammation to decreased fat to increased vasodilation, increased capillaries, muscle growth, obviously, just so many different things, stuff related to mitochondrial growth, to yeah, so many different factors: insulin resistance and insulin sensitivity, muscle or muscle glucose uptake, so many things. And the thing that I really get at, and that I'd love us to all get at by the time we're done with this today, is that your body is designed to exercise. It is 100% designed to exercise. And so when it's not optimally functioning, and diseases ensue. When you are exercising, you're optimally functioning, and those and that wards off many, many diseases, and even goes against diseases that people already have. So let's get into it. So, number one cause of death in the U.S. is cardiovascular disease. Okay, in the U.S., the last round of statistics that came out showed 634,000 deaths related to cardiovascular disease per year. In 2017, that was the latest stats that I had on this. That means one death every 49 seconds due to cardiovascular disease. Okay, in 2015, 9% of the population had type 2 diabetes, and and then actually 35% had what's called pre-diabetes. Okay, so huge numbers here for both cardiovascular disease and type 2 diabetes. Okay, so when you look at those all those deaths, this is just a pie chart that looks at that in percentages. Okay, so if you clump together heart disease here with some of the other ones, so heart disease, stroke, um, those two will clump together to get you the cardiovascular disease deaths. You can see the close second is cancer. That one's actually decreasing at this point. The one that's sad and very scary in our country um, is suicide, which is in the top 10 list here as well. 1.6% of the deaths. That means about one suicide every 10 minutes in our country. So very, very sad um, realities there. When you look at the same pie chart, instead of percentage, just number, that's all this shows. And so, but then when we look at within those cardiovascular disease deaths, what actually is the cause of death, we can see very clear that over half of those are what's called coronary artery disease. So this is a heart attack, right? Also known as an MI, or myocardial infarction. But then there's a good chunk of stroke, heart failure, hypertension, and other cardiovascular disease related deaths. So really, it's an MI that kills over half of those people for that leading cause of death, and then stroke is behind that. So, common risk factors for cardiovascular disease and type 2 diabetes. Normally in class we would walk through this together, and so I'll just write in a few here. So obviously diet, And under diet, we have saturated fat. Okay, we have down here for diet, we have sugar intake. Okay, we have definitely trans fat intake is huge. Obviously, sedentary lifestyle. That definitely counts for both of these. Genetics are huge on both of these. Number one risk factor for both is age, for sure. Okay. Yeah, smoking is huge for both. Okay, we can talk about blood pressure, talk about cholesterol levels, about waist circumference, which really gets at visceral fat. And we'll talk more about that later. That definitely is down here as well. Lots and lots of factors. You could Google this, look it up. There's lots and lots of other factors here, but these are some of the strongest ones. Okay, this graph nicely shows some common risk factors. So smoking, body mass index, physical activity, diet, cholesterol, blood pressure, glucose, and it shows the green chart. Green bar would be the percentage of our country that when they did this back in 10 years ago or 8 years ago, percentage of our country that was in the ideal range for this. Red would be intermediate, and the orange or yellow is poor. Okay, the one that's really striking that nobody's in the ideal is diet. That was interesting, right? Less than 1% of people are in diet. The one that's sad for us as kinesiologists is the physical activity one. Maybe half of people 20 to 49 are meeting the guidelines, but once you get up over 50, it's probably only about a third of the country that's doing that. And that seems like one that should be a modifiable risk factor, right? We should be able to just say, well, just do it, just exercise, right? But we find out that it's not. It's not that easy just to tell people to exercise because it's good for them. Okay, so we're going to dive into a little bit of physiology here, and really it's pathophysiology, looking at the progression of atherosclerosis. Okay, and so when you're thinking about your concept maps, you have the option to choose atherosclerosis or glucose control. Okay, and in each of those, you have to outline the pathophysiology, and then show how exercise changes that pathophysiology. So what I'm about to run through here is a very detailed description of the pathophys of atherosclerosis, and this is something you would want to have in your concept map if you chose that one. Okay, so it all starts with endothelial dysfunction. So remember, we have this small endothelial cell layer that lines all of our blood vessels. One of the jobs of that tissue is to produce nitric oxide. Okay, and we can see that that tissue is not functioning well when we have decreased nitric oxide. Okay, so all of this, the very first step in the progression of atherosclerosis is a decrease in the production of nitric oxide. And the thing that makes nitric oxide is an enzyme called eNOS, endothelial nitric oxide synthase. Okay, so in endothelial dysfunction, we see decreased eNOS levels, which leads to decreased nitric oxide levels, which one thing that does leads to inability to properly vasodilate, because nitric oxide is a vasodilator, so we can't open up blood vessels as well. Okay, another thing that does is dysfunctional eNOS, instead of producing nitric oxide, produces free radicals. Okay, free radicals bind to lots of things and cause damage, but one of the things they bind to is LDL that's built up in our blood vessels, and then they do something to that LDL called oxidize it, okay, which would be pull an electron off of it, okay, and that by pulling an electron off of it, that oxidizes it, and that makes it look like a foreign invader in our cells, in that, or in our tissues, and that causes our immune system to attack it, especially our macrophages. So that's an important chain of events there. Okay, and then the third thing that we see with decreased nitric oxide in step 2 here is that normally nitric oxide inhibits the expression of these little molecules called cellular adhesion molecules. And there's two of them here, VCAM and ICAM. There's another one in the image you'll see in a second called E-selectin. Okay, all of these, think of these as little flags that cells send out on the surface of the cell into the blood to call in the immune system. They say this is a kind of like a flag saying we need help down here, we got a problem. Okay, and so when there's plenty of nitric oxide being produced, that nitric oxide inhibits these little molecules from coming out. But when there's not as much nitric oxide coming out, we don't inhibit that. So less inhibition of these cellular adhesion molecules. So what that leads to is that stimulates platelets, macrophages, and T cells to all aggregate around that tissue as well as migrate into the tissue to start the inflammatory process. Okay, so this leads to immune cells aggregating inside of our blood vessel walls. Okay, those immune cells release pro-inflammatory cytokines. Okay, and then so we see increased pro-inflammatory cytokines. We also see decreased anti-inflammatory cytokines. That leads to systemic inflammation and chemotaxis, which just means all those leukocytes or white blood cells coming to that area. So a bunch of white blood cells coming to that area, they're all getting called in to help. Okay, so we see that. We also see immune cells releasing things called growth factors. Again, this is a normal part of the healing process. When you have damage in an area, we want those immune cells to come in, clean it up, release growth factors, stimulate the cells to lay down scar tissue and heal the tissue. But instead of that happening in a nice way, we get laying down of collagen, but that also stimulates smooth muscle cells to migrate up from the middle layer of the vessel into the intima layer closer to the blood. And so we start getting this accumulation of scar tissue and smooth muscle cells. We'll see that on the next slide, or next two slides. Secondly, those macrophages that are called in by those cellular adhesion molecules, when they interact with LDL, especially oxidized LDL, they love that stuff. They're gonna eat it up, and they eat so much of that oxidized LDL, they actually get engorged and become what's called a foam cell. And then they do so much of that eventually destroys them. And then they're just stuck there, this big fatty dead cell. So now we have part of our plaque being formed, which is made up of dead macrophages, collagen tissue, as well as those smooth muscle cells. And then we have this hard, necrotic, fibrous plaque with a bunch of fat in the center, which was that LDL. And that's really the formation of the plaque. Now that we've got the plaque, that plaque progresses to get to a big enough size to where it can actually start cutting off blood flow to that area, which can lead to more cell death, which leads to more necrotic tissue, and eventually rupture of that endothelial wall. And that's when things get dangerous. Okay, and there's a few factors that lead to a higher chance of that endothelium rupturing. Number one is something called MMPs. Think of these as like little Pac-Man. Little Pac-Man comes in, eats up some of the collagen, smooths out the tissue. This is all, again, a normal part of the healing process where we're supposed to be able to clean up that collagen, smooth it out. But in this case, it's cleaning up the collagen and breaking down the plaque in such a way that it makes it more unstable, higher chance of rupturing. Secondly, when a plaque starts to get its own blood supply, that's what angiogenesis is. Gets its own blood supply. Okay, so blood vessels start coming in, feeding that plaque. That leads to a high, not change, but chance of rupture. Again, this is mediated by a chemical or molecule called integrin. We'll see that on the next slide as well. It's another form of an adhesion molecule. Okay, so if these two things are happening, then we're more likely to rupture. So when that rupture does happen, what that does is that exposes some of that collagen and other stuff that's inside the blood vessel wall to the blood, that immediately stimulates the blood clotting process. And the blood clot is made up of fibrin, okay, um, and so fibrin and platelets all form this big blood clot, okay, and that narrows the artery even more, and then eventually that clot can bust loose, and then it can start rolling down the blood vessel. If the blood vessel is small enough for it to just get stuck right there, then it's going to block off the blood flow right there, and no more blood's going to get down. If it's not small enough, then it's going to keep rolling down till it finds itself in a small enough blood vessel that it gets stuck in. If that happens to be in the brain, that causes a stroke. If that happens to be in the heart, that causes a heart attack. And this is the cause of most heart attacks and strokes. Okay, so that's the progression. This slide here is a very nice depiction of that progression of atherosclerosis. So this is the healthy right here. Okay, that's the healthy vessel, and then we're working ourselves this way. This is looking at endothelial dysfunction. Okay, the first step. All right, so we see decreased nitric oxide production. We see a buildup of LDL. Okay, this LDL is also going to be getting oxidized. Because of that decreased nitric oxide, that's going to lead us right over here to step 2, which is going to lead to an increase in these adhesion molecules. Right? Increasing these adhesion molecules, that's going to bring in the immune system. Right? So that leads us right here to bringing in monocytes. Monocytes eventually turn into macrophages. Once they come into the blood vessel wall, they turn into macrophages. That's what these are. Those macrophages start engulfing this oxidized LDL. T cells also come in. When they engulf enough of that oxidized LDL, they die and turn into a foam cell. This big cell is just full of fat. We're going to see growth factors being released here too. Right, those growth factors are causing the neighboring cells to release collagen. Right, as well as those growth factors are stimulating smooth muscle cells to migrate from down here where they're supposed to be in the media layer. They migrate all the way up here to where they have no business being at all, and they become part of this plaque. Okay, so now we see this next step, we see some dead cells. That's some of those macrophages are dead. We also see the induction of those MMPs. Look, told you they look like little Pac-Man. So they're chewing up all this collagen, but that collagen is becoming less stable, and the plaque's becoming less stable because of that. So then we move over to this step. That's really where we start seeing this smooth muscle cell aggregation and all this collagen aggregation. And you can see these big foam cells now here. Moving over into this next step, we see integrin, which is a little molecule that causes the formation of new blood vessels. Okay, those new blood vessels are going to be what's leading to, so the MMPs and the integrin are what's leading to a more likely chance of rupture. Okay, so eventually this plaque ruptures. That's what's shown right there. That exposes things like tissue factor and collagen to the blood, which automatically stimulates the blood clotting cascade, which results in fibrin, which is what clots are made up of, also makes platelets aggregate, turns it into a thrombus. Okay, that thrombus can bust loose and go rolling down the artery, cause an MI or a stroke. Okay, so that's the basic flow of this. The amazing thing about this is we are going to see how exercise changes every single one of these factors as we move forward. Okay, so let's do it. All right, so how does exercise improve endothelial function? First of all, I should probably answer the question of what causes endothelial dysfunction, because we didn't really say that. We just said it happens. Right? But dysfunction would be caused by smoking, okay, sedentary lifestyle, okay, dietary factors, high blood pressure, high LDL. Wait, it's all those risk factors for cardiovascular disease, right? So all of those risk factors for CVD are what cause endothelial dysfunction. Okay, so how does exercise change this? exercise leads to something called increased shear stress. Okay, increased shear stress is instead of blood just, if we've got a blood vessel here, blood is kind of just normally just flowing through. Okay, but then when we start exercising, that the blood pressure increases, so that churns blood up. Blood starts churning, kind of spinning around in here, and it's pushing out on the walls, right? Pushing out on the walls. That pushing out on the walls is called shear stress. And what we see with that is that shear stress leads to first of all, that stimulates mechanoreceptors on those endothelial cells, and that activates them. And those mechanoreceptors eventually lead to activated eNOS, which leads to increased nitric oxide release. Okay, that's kind of the acute effect, right? Acute effect. But then the chronic effects would be increased production of eNOS, which also means increased nitric oxide availability. And then if we've got increased nitric oxide, then we've got decreased adhesion molecules. All right, we've got increased vasodilation, which that's going to lead to a decrease in blood pressure. Okay, this is going to lead to a whole chain of events, which pretty much decreases the progression of plaque buildup. Okay, so there's some information and a lot of studies out there on what type of exercise might be the best for improving endothelial function. A lot of research looks at HIIT versus continuous exercise. Kind of the same question of does intensity matter and why. So the idea might be that higher intensity, increased intensity, then increased shear stress. All right, so if we've got more shear stress, then maybe a greater effect. Seems to be that way with some studies, but we're not sure. Let me walk you through one study which was done on this, which was my dissertation project at ASU. And so what we did, we were the first study to really look at this in obese individuals who are sedentary. So we had 18 of them finish the study. They did 3 sessions a week for 8 weeks of either HIIT or continuous. Okay, the HIIT looked like 1 minute on, 1 minute off, 10 times. That 1 minute on, they got to 90 to 95% of their maximum heart rate. This was done on the bike, on a stationary bike. Total exercise time was a little over 11 hours. Continuous group did 30 minutes at 70 to 75. Total exercise time was 16 hours. All right, so quite a bit shorter in the HIIT group. Okay, and the main outcome that we tested in that study was something called flow-mediated dilation. Flow-mediated dilation is a non-invasive way to measure endothelial function. We have an ultrasound machine in the lab that we can do this test on as well. So the way that the test works is you get an ultrasound machine and you hold it right here on their brachial artery. Okay, and then you go ahead and put a blood pressure cuff around their forearm distal to that brachial artery. And the first step is to measure baseline artery diameter. So you get that blood pressure cuff, or you get that ultrasound machine, get a nice visual of the brachial artery. We have some software that's going to measure that. We measure that for a couple minutes, get a baseline, so get a resting level, okay, which is right here. The resting diameter would be like this, right? And then we pump that blood pressure cuff up. So we occlude the blood flow for a full 5 minutes. Okay. After that 5 minutes, we release the cuff. The body tries to overreact and send a bunch of blood down that artery, which creates a bunch of shear stress. All right. So a bunch of shear stress. And then that shear stress causes maximal release of nitric oxide, maximal vasodilation. And we wait about 3 minutes after, still measuring the artery. And we want to see the peak artery diameter, so dilation diameter, and we just compared this, the resting diameter to the dilation diameter, and the FMD number, flow meter dilation number, is that just percentage increase. So 7% looks like about normal. And the wild part about this measurement is for every 1% decrease under 7%, we see about a 13% increase in CVD events, which equals strokes or heart attacks. So a very predictive measurement. Okay, this is kind of a schematic of what that test looks like. So this would be where the blood is, inside the artery. Okay, it's flowing this way. Once we pump that cuff up, release the cuff, it creates shear stress, right? So we got blood churning around in here. That activates these little mechanoreceptors. Mechanoreceptors stimulate this whole chain of events, which leads to the activation of eNOS. eNOS produces nitric oxide. Nitric oxide doesn't go to the blood. Nope, it goes down here to the smooth muscle and causes smooth muscle to relax and causes vasodilation. Okay, this is a little image. Yeah, that's not going to work for us. I have 2 videos here that aren't going to work playing on my iPad here, but that's okay. I think you'll get the idea. This is our ultrasound image of a brachial artery. Okay, this is the actual artery itself here, right? And we have the special software that measures the distance between 2 points thousands of times and gives us our average distance between all of those points to give us diameter. Okay, so it's a brachial artery. Also has a little Doppler probe right here, and that Doppler probe is going to tell us velocity of the blood flow. So every time this pumps up, we see the blood's going at about 40 centimeters per second. There's also always a little bit of backflow with each beat of the heart. Okay, and then this is the actual measurement part of it down here. This is the diameter, 0.22 centimeters or 2.2 millimeters. This is actual flow, and this is one's flow in mils per minute. The other one is another way to express flow. So when we do this test, we'll see resting diameter here, and then if I was able to play the video, you would see these kind of coming up like this. Would pretty much do this, and then it would come back down. Blood flow would shoot way up when we release the cuff, and then it would come back down. Okay, and what we would do is we measure this diameter versus this diameter. We measure that distance between the two, and that's our percent FMD. And so we can see that on the next slide exactly what happened. Here's that baseline measurement. Here's the peak measurement. So the baseline was 2.19 millimeters. Peak was 2.28 millimeters. And that FMD peak was about 4%. This was an obese person who was sedentary at the beginning of my study, so they had a severely impaired endothelial dysfunction to begin. So that was the primary outcome of my dissertation study, and here's what we found. So FMD improved from 4.5% in the HIT group at baseline to 8.2 after 8 weeks. We can see that nice clean increase here. What we saw in the continuous group is it almost looks like it goes down, but this is a non-significant decrease. So the continuous group didn't really improve flow meter dilation at all. And we published this in 2016 in the Journal of Applied Physiology. Okay, the other interesting finding here was that resting artery diameter, the one that we measured before we pumped the cup up, we saw in the continuous group that actually increased, and that was a significant increase. In the HIT group, this did not change. So what we see with this is continuous led to what we call a structural adaptation, which means the artery gets bigger. Okay, whereas HIT led to a functional adaptation, which means it can vasodilate better. And that's what we saw, and that was our conclusion. So interesting stuff for sure. There we go. Okay, so we also we've seen quite a few other studies now looking at HIT in other kind of at-risk populations or even disease populations. The one that came out in 2007 that just kind of shocked everyone was this one by a Norwegian group from main author of Ulrich Wisloff. He had 27 patients who had a heart attack post-infarction, and then now they all had heart failure. He made them do 12 weeks of 3 days a week of HIT or continuous. And the HIT here was actually the 4x4 protocol. So meaning 4 minutes on, 3 minutes off, 4 times. Usually considered harder than the 10x1. And what they saw was HIT doubled endothelial function, increased their VO2 max by 46%, increased ejection fraction by 35%, and decreased pro-brain natriuretic peptide by 40%, which is a marker of heart failure. And this is the graph of their FMD. Everybody increased, very strong. Another colleague of mine, Sid Angadi, who's a professor at ASU, I was in the PhD program with him. He did his dissertation study was a 4-week HIT intervention versus standard cardiac rehab in heart failure patients as well. His main outcome, just in 4 weeks, which was really only 12 sessions of HIT, they have a 3-point heart failure criteria scale, or heart failure severity scale would be the better way to say it. And what they saw in the HIT group is that dropped 1 full point in the heart failure scale. That was a significant drop. There was no change in the moderate group in just those 3 3 weeks, 4 weeks. Okay, so let's talk about all those different risk factors and factors related to cardiovascular disease that were related to endothelial dysfunction and exercise. So high blood pressure is one of those. The thing about high blood pressure is there's an acute effect and a chronic effect. So one acute bout of exercise can decrease your blood pressure by 13 millimeters of mercury for up to 8 hours. So that's huge. So if you exercise every day, then you got low blood pressure for most of the time. But let's say you can only do a 10-minute walk. That's okay. There's been studies that have looked at 1 30-minute bout of exercise in the afternoon or morning, compare that to 3 10-minute bouts of exercise, and because of this acute effect of exercise, that fractionized exercise broken up into chunks is actually better for decreasing your blood pressure. Okay, that's the acute effect. Chronic effect, we expect to see about something like this, about 6 to 7 millimeter decrease in both systolic and diastolic. And a lot of the stuff looks at, well, how hard do you actually have to exercise? Is intensity a factor? Is HIT better than continuous? And no, it doesn't seem to be actually moderate intensity exercise, which would be like a brisk walk, is probably actually the best for hypertension, and volume seems to be the number 1 factor instead of intensity. So that's blood pressure. And so obviously if we decrease blood pressure, if we decrease BP, then we improve endothelial function. And that's going to start us at the very beginning, so that should definitely be part of your concept map. What about dyslipidemia? This is blood cholesterol levels, right? So physical inactivity has shown to decrease HDL levels by about 4%. HDL is the good one, the one we want to be high, right? Exercise will change your total cholesterol and your LDL levels, both bad ones. We can see those decrease by about 10 to 15%. Exercise can increase HDL levels by quite a bit, 10 to 17%. Exercise can decrease triglycerides by 10 to 20%. All of these are related to atherosclerosis and buildup of plaque in the arteries. Okay, what about exercise on inflammation? Okay, so we've got aerobic exercise. There's some evidence that aerobic exercise, a lot of evidence, will decrease most of what's called pro-inflammatory cytokines. These are all little chemicals that activate the immune system. Okay, so interleukin 1 beta, interleukin 6, C-reactive protein, tumor necrosis factor, interferon gamma, all these different ones are activators of the immune system. Exercise decreases these. Okay, and it also increases the anti-inflammatory ones. Interleukin 4, interleukin 10, and adiponectin. These are all increased with exercise. So this article right here by Balducci is a fantastic article that shows this. When you read the review article that I was a part of writing at the end of the semester, we reviewed this one exactly. But exercise has a full anti-inflammatory effect. Okay. What about exercise on blood clotting and plaque stability? Aerobic exercise has been shown to decrease mediators that lead to plaque rupture and instability. We were just talking about those. What were they? Right there are those MMPs. It was the integrin. Also angiotensin 2 wasn't mentioned before, but that's one of the angiogenic factors as well. Exercise decreases these, which makes the plaque more stable. Okay, so more stable, which would mean decreased risk of rupture, which means decreased risk of clot, which means decreased risk of MI or stroke. Okay, and then we also see that some factors in the blood change with exercise too, so the factors that lead to clot formation. So we get decreased levels of fibrinogen, decreased levels of PAI1. That one is kind of a tricky one to understand. It's called plasminogen activator inhibitor. Okay, so plasminogen activator inhibitor. So it's a double negative because it inhibits an activator, and we're talking about decreasing. So we're decreasing the inhibition of an activator. Just believe me when I say that when we have decreased levels of PAI1, that leads to less clotting, right? So that decreases our risk of a clot happening. Okay, so all those things are caused by exercise. Okay, so now what you can do on your own, what I'd like you to do, is I'd like you to go back to that color figure that showed the effects of, or the progression of atherosclerosis, take all the stuff we just talked about and plug in how exercise changes all of those effects of every step in the progression of atherosclerosis. And I'm going to challenge you to find where exercise changes every single one of those factors. And that's exactly what you want to do with your concept map. All right, so you may want to pause it, take a little deep breath, take a breather, but I'm going to keep rolling here and look at type 2 diabetes now. Okay, so we'll move right into type 2 diabetes. There's three main factors that lead to high blood sugar or hyperglycemia. Okay, the one that we always think of and have been taught that type 2 diabetes is caused by is this decreased insulin signaling, or really, this would be insulin sensitivity. All right, so decreased insulin sensitivity. Okay, this is mainly by the skeletal muscle because the skeletal muscle takes in about 75% of the glucose. Okay, this is partially related to mitochondria not functioning well, and certain types of fat buildup in the muscle. Okay, so that's number one factor. But number two, we also have a decrease in beta cell function. Beta cells are in the pancreas, right? This is the pancreas. They stop releasing as much insulin. Now we typically think of that being more type 1 diabetes, that the pancreas stops doing a good job of releasing insulin because it's destroyed by our immune system, but type 2 diabetes is also related to this. In fact, by the time type 2 diabetes is diagnosed and you actually see high blood sugar, most likely you already have only about 40% of your beta cells left. So we diagnose the disease way too late. That'd be something we can talk about at another time. And then the third factor is called increased HGP, which is hepatic glucose production. Okay, so your liver is responsible for maintaining your blood glucose levels when you're fasting. Okay, so when you sleep at night and you haven't eaten for a long time, you're not taking in any glucose, your liver's job is to break down some glycogen, turn that into glucose, and release it into the blood to maintain your glucose levels. Its job is also to stop releasing glucose when you eat. So when you eat that glucose levels rise, your pancreas senses that, releases insulin. Insulin goes to the liver, tells the liver, all right, stop releasing glucose because we don't need it anymore, right? So this is the insulin sensitivity in the liver. But in type 2 diabetics, that insulin goes to the liver, tells the liver to stop releasing glucose, and it doesn't do it. It just keeps releasing it. So we have decreased insulin sensitivity in the liver. This is highly related to visceral fat, which we'll talk about in a second, which is related to the portal theory. So if you do your concept map on this one, you need to address all three of these factors in the pathophysiology and in the effects of exercise. Okay, so let's talk about visceral fat first. The problem we see with visceral fat is that most of us are in what's known as a positive energy balance a lot of the time, right? Our energy intake is greater than our energy expenditure. Okay, so what the body does with that, the body's very good at holding on to calories. It's not going to let those calories go. They're just too important. So it's going to pack those calories into fat, into our, first of all, our subcutaneous adipose tissue. Okay, so right here, subcutaneous adipose tissue. But there's only so much that can expand. We can only expand that so much, and once those cells get full, then we're going to start sending our lipids other places, and we call that lipid overflow. So we get lipid overflow into the pancreas, into the kidneys, the muscle, the heart, the liver, and all throughout our visceral space, which is all this space inside of our abdominal cavity. And this fat buildup is bad for this tissue. In the pancreas, that leads to breaking down of beta cells and loss of ability to release insulin. In the other tissues, it causes insulin resistance and inflammation. All right, all of these factors lead to what's known as increased cardiometabolic risk. Okay, all of this also leads to high risk of type 2 diabetes, and then directly connected to cardiovascular disease. Okay, so connected directly to this is the portal vein theory. So the portal vein is that big vein that goes from our digestive tract and takes all those nutrients we absorb from our digestive tract, dumps them into the liver so the liver can process those. Okay, but the problem is we have this big depot of visceral fat which is right next to our portal vein. And visceral fat is known to be very active, constantly releasing fats. And when it releases fat, the visceral fat depot right by our portal vein, it dumps fats right into that portal vein, which go right to the liver. The liver ends up storing all of that fat, and we get increased exposure to free fatty acids, which leads to that insulin resistance in the liver, fat deposition, lipotoxicity, which means destruction of those cells, and problems with metabolism in the liver. So this is the portal vein theory. So if you ask me what would be more of an important thing to measure, total body fat measured by something like the bod pod, which costs about 50 grand, or just waist circumference, which you can do with a tape measure, which costs 50 cents to $1. Hands down, waist circumference is a more important measure of health because of that visceral fat. Waist circumference is not the same thing as visceral fat, but it's highly related to it. So visceral fat should really be known as a new vital sign. Waist circumference is an easy way to get at that. Okay, this slide, you don't need to know the details, although you could include these details in your concept map if you wanted to, but this is the connection between type 2 diabetes and cardiovascular disease. At least it's one of the many connections. Okay, what we see here is insulin binds to an insulin receptor. This is the healthy one. Okay, it leads to all these different events here. One of those events is GLUT4 translocation and glucose uptake. That's the one we know of, normally talk about. But also look what happens. It activates eNOS, that same eNOS we were just talking about, which leads to nitric oxide production, vasodilation, right? We know nitric oxide does all kinds of other things that decrease inflammation and whatnot. Okay? But look what happens when that's not working well in type 2 diabetes. Type 2 diabetes here, all these things aren't working so well. So instead of an increase in GLUT4, we get a decrease. Instead of an increase in eNOS, we get a decrease. So less vasodilation, endothelial dysfunction, coronary heart disease, hypertension, atherosclerosis, all of these things. So there's a strong link between the two diseases. All right, let's talk about how exercise affects type 2 diabetes. All right, so when you do this one in your concept map, the insulin sensitivity side, or that glucose uptake in skeletal muscle, you've got to look at both acute effects and chronic effects. Just like we have with blood pressure, we've got that here on insulin sensitivity. So up to 85 to 90% of our glucose disposal happens in skeletal muscle. So skeletal muscle is a huge tissue that's a part of type 2 diabetes. Exercise both acutely and chronically increases GLUT4 receptors. GLUT4 receptors are the gates for glucose to get into cells. All right, so the acute effects can last up to 72 hours. So one bout of exercise can increase your sensitivity to insulin for 72 hours and decrease your glucose levels for 72 hours. That's 3 days, right? So if you know a type 2 diabetic and they say, oh, there's no way I can exercise 5 days a week. That's just way too much. It's asking too much. Then tell them to exercise 1 day a week. Then they'll have 3 days of improved glucose control, right? That's a very important thing to know. This article, the Rockwell one, is one I've given you on Canvas. This image comes right from that. So use that to get into the details of how this works. Okay, so the acute effects are mediated by AMP kinase and calmodulin, and then maybe this other APKC one here. So what we see inside of a cell, calcium release, we know that's related to exercise and muscle contraction, right? That's going to activate this whole calmodulin pathway, which leads to GLUT4 coming to the surface, which would lead to glucose coming in. Secondly, this ratio of AMP, which is just ATP minus 2 phosphates, right? As we increase that ratio, which we do with exercise because we're using ATP, and we increase that ratio, that activates a similar pathway, leads to GLUT4 coming to the surface. So very important things for the acute effects. What about the chronic effects? Chronic effects of exercise, also from the Rockwell article, there's 3 main things that happen. Exercise, again, using that AMPK and the calmodulin pathways that we see here, calmodulin, AMPK. Both of those lead to PGC1 alpha, right? So you've got to have PGC1 alpha. Okay, PGC1 alpha is a mitochondrial activator. So that leads to fiber type transformation, so moving towards type 1 or type 2A from type 2B. Leads to mitochondrial growth, leads to more GLUT4 protein. So we see those 3 factors here chronically. Okay, this leads to about a 25% improvement in insulin sensitivity. So what you want to do in your concept map is connect all of these 3 factors to how does that decrease glucose. So take it a little bit further down the chain. How would each of those 3 things decrease glucose levels? Okay, so what about HIT in clinical populations, people with diabetes? A couple great studies came out in right around 2011, 2012 by a group in Canada that used 24-hour glucose monitoring, and they just did 1 bout of high-intensity interval training in type 2 diabetics, measured their blood glucose for 24 hours straight. We see average glucose levels on the day that they did no exercise versus the exercise day dropped significantly. This is the actual glucose tracing of the day, no exercise day here, and then the dotted line is the exercise day. You can see those drops in glucose levels all day long. Very, very important. Average about 13% lower on their average glucose levels. And they extended that study to do 6 sessions of HIIT, so training for 2 weeks, really, right? Just 2 weeks, 3 days a week. They did a muscle biopsy to measure GLUT4 levels in those subjects. 369% increase in the level of GLUT4 in their muscles, which is 6 sessions of HIIT. So incredible effects of HIIT in diabetics. What about exercise? So that's the effects of exercise on insulin sensitivity and skeletal muscle. What about the effects of exercise on the liver? Okay, that's the third factor that I talked about that controls blood glucose. High visceral fat, as well as sedentary lifestyle, is definitely related to buildup of fat in the liver. Okay, exercise has been shown to decrease visceral fat. If we decrease visceral fat, then we can decrease fat in the liver. So exercise can also decrease fat in the liver, which improves insulin sensitivity, which leads to that proper inhibition of glucose release. Right? So when insulin is released because you just eaten, insulin should go to the liver, tell it to stop releasing glucose. But if there's insulin resistance there, it doesn't do that. Exercise improves that function. There's some evidence that show that HIIT may be more effective for visceral fat reduction. One of the reasons for that is that visceral fat cells have an increase in epinephrine receptors versus just subcutaneous fat. The effects of epinephrine on fat cells, when epinephrine binds to it, it causes them to break down the fat on the inside and release that. And so if there's more receptors, you'd think that higher intensity exercise, which leads to more epinephrine release, more stress in the body, would lead to a greater breakdown of the fat in those cells. That's a possibility. And then the more carbs and glycogen we burn during exercise because of high intensity exercise, that means there's going to be a period of time where we're replenishing that glycogen, which means we're burning fat post-exercise. What about exercise on the third factor, which is beta cell function in the pancreas? Right? This one's a lot harder to measure because the gold standard measurement of this is actually full beta cell mass in the pancreas, which you have to take the whole pancreas out to do that. So there's been some studies in rats, which they see aerobic exercise in rats can lead to about a 40 to 50% increase in beta cell mass. And then we see higher levels of production and storage of insulin in those rats. We can't do these studies in humans. The human studies that we do can look at some other factors, which are kind of other measures of insulin secretion ability, and they see improvements in beta cell health after about 2 to 3 months of aerobic exercise, but only in people who still were able to secrete some insulin. Type 2 diabetics that are long-term, very unhealthy, type 2 diabetics, end stage, they don't release insulin anymore. Then they become like type 1 diabetics. Those types of people did not improve their insulin production with aerobic exercise, only the ones that could still release some insulin. So that's the beta cells. One last bit here on the effects of exercise on visceral fat. Overall, exercise decreases visceral fat. This is a meta-analysis that looked at the effects of exercise on visceral fat. The key with these graphs is this is the overall effect down here. We want that to be in the negative, right? So showing that yes, all these studies put together show that exercise does decrease visceral fat. They tried to look at moderate intensity up here versus higher intensity down here. They didn't see a difference in those, but most of these high intensity studies were not HIIT. They were just more vigorous exercise. So we definitely see an effect of exercise on visceral fat, but not, no strong evidence that HIIT is better for that yet. Okay, so what I'd like you to do now is take that information we just went through and look at, plug in the effects of exercise on the pancreas, effects of exercise on the liver, effects of exercise on the skeletal muscle and insulin sensitivity, and that'll be what you look at for your concept map as well. Okay, the place you're going to want to focus in on your concept map, if you're doing this one, when you go to find new articles on this, will be this one up here, the pancreas, and this one here on the liver. The Rockel article I gave you gives you a lot of information on the skeletal muscle, but you'll need to find some more information on the pancreas and the liver. All right, guys. Hope you stayed with me for that whole thing. Feel free to go back and dive back into that as you're preparing your concept map. But that's all I got for you.